here and take a look at a couple other questions here. First of all, let's answer a couple of these questions. Is 57 mu or x bar? Number 57 in this description, is that the population mean or the sample mean? That's the sample mean is x bar. Good. It's a statistic, not a parameter. Five. If five is sigma, is that sigma or standard deviation in this case? That's sigma, right? Because we said we knew the standard deviation for the population. That happens to be sigma, which is a parameter. Calculate standard error, repeated biblical. We just did that. Calculate the 95%. We did that. If brand B is known to produce 95 loads per bottle, can you say with any certainty that brand A goes further than brand B? Let's see. We said 95 is wrong. Can't be 95. Too big a difference. I'm going to say produces, what was our confidence interval again? I forget what our confidence interval was. 56 to 58. 56 to 58. So I'm going to say 59. Oh, I reversed the numbers. It's 59. If brand B has a product known to produce, in other words, it's not a sample. They know, they tested every bottle, and they know it's the population mean is 59. Can we say that brand B goes further than the first one we did, brand A? That brand B goes further than brand A. Okay, can I say that they're different? In other words, okay, so I can say that they're different, right? Because I'm 95% sure that the true population average for the amount of washes you get out of this brand A is 56 to 58. And if I compare it to a known population mean of 59, I can see that there's a difference. I'm 95% sure, since this is outside of the confidence interval for A, I'm 95% sure that brand B will actually do more loads than brand A. Okay, there is 5% chance I'm wrong, and that brand A could do 59, but based on our calculations, I can't say that. I can reject the idea that they're the same. What I'm doing there is a little bit simpler than comparing two groups. I'm just comparing a known mean for one population to a statistical mean from the other population. But I'm still looking to see that it's outside of either within the confidence interval or outside of the confidence interval to say whether there's a level of confidence of 95% that I can say that they're different. Not in love. That's a bad example. I don't like that example. Okay, so now I'm gonna at this point, I am gonna pull up Excel for a moment. I'm gonna come back to exercise 4. I'm gonna pull up an exercise on Blackboard from Excel. Let me see if I can't find it. Okay, descriptive statistics example. Okay, here is my example of a 30 people that have been sampled. I'm not going to hazard a guess as to what this is with these numbers. What might they represent? Say they're blood sugars. For whatever argument, they're really just numbers. The sample size is 30. Let's calculate the mean of this sample. That's going to be equal to average. Okay, and I'm going to find the average for all of these values. It's going to be A1 through A30. And the average is 69.8. Let's find the standard deviation of this group. Okay, I'm going to find the standard deviation. That's going to be equal to 3.51. Now, let's calculate if we took sample sizes of 30 over and over and over again, what would be the standard deviation for that sample distribution, repeated samples of size 30? Well, that's going to be equal to the standard deviation of the population divided by the square root of n. Do I know what the population is? Do I know what the standard deviation of the population is in this case? All I know is the standard deviation of the sample, not of the population. I'm going to cheat right now, and I'm going to say that the standard deviation of the population probably approximates the mean of the population. That's a cheat. Later on, we're going to introduce a correction factor for using the standard deviation population, the standard deviation of the sample, instead of knowing the standard deviation of the population. I'm going to click on there and I'm going to divide it by the square root of 30. Square root of 30. And the standard error is equal to 0.0649. So this is our standard error. Again, it's a bit of a cheat because I didn't know the population standard deviation sigma, which I just told you need to know to do this, right? Later on, we're going to be looking at a correction for that. But for right now, I'm going to live with this. So what's my lower confidence interval going to be? Well, it's going to be equal to x bar minus 1.96 times the standard error. So it's going to be 68.54. What about the 95% confidence upper bound? That's going to be equal to 69.8 plus, and I see, there's questions there, so I'm going to get to them in a second, 1.96 times the standard error. My confidence interval, my 95% confidence interval, is 68.54 to 71.58. Now, I know that I cheated here and that, I got to make up for that cheat. And the way I make up for that cheat is by making the lower bound a lower number and the upper bound a larger number. How much I expand this range depends on how accurately I think I know the standard error, population standard deviation. And the larger the sample size is, the more confidence that I have a good idea of what standard deviation is. 30 is not a small sample, but it's certainly not a big sample. I would have known it with more confidence if this were 100 or 200 or 500 people randomly selected and so on and so forth. But this is what I get if I ignore the fact that that the standard deviation is not sigma, right? It's just a standard deviation for those numbers that were in my sample. But it's a little bit, if I really calculated and made up, for the uncertainty in doing this, in using this, then this range would have been a little bit wider. Well, I'm going to do something now with another example of this, which is the same example, except I'm opening up these numbers, values in SPSS. SPSS automatically has built into it calculations that would make that correction for you based on the sample size. We're going to learn about that later. It's something called a t-score, but we're going to learn about that later. Instead of using a z-score for the width, figure out the width of your confidence interval, use something called t-score. But that's ahead of the game now. We don't need to know that necessarily right now. Okay, I'm going to go up to Analyze. I'm going to go up to Descriptive Statistics. I'm going to go to Explore. And I'm going to look, they didn't give it a variable name. It's stuck in V1 because I didn't give it a variable name, right? It's the same numbers as I had before. And I'm going to say, okay. Okay. It's going to go ahead and calculate all of the statistics that we're usually interested in, the mean and so on and so forth. But it also calculates a standard error. Okay, what did I calculate standard error was before? See if I can't find it. Let me get this out of the way. I calculated the standard error was 0.06421. It's using for the standard error. SPSS is using 0.0642, probably more decimal places, right? So it's using a number that's pretty close to mine. It's saying that the confidence interval is 68.49. I got 68.54. Notice that if we had got that extra decimal place, I would have guessed it was bigger than that one that I got. It might have been 3 or 4 or 9. It made it bigger. You don't see it there, but it's using a bigger number. How do I know it's using a bigger number? Because the lower bound is smaller than my number and the upper bound is bigger than my number. It's correcting for the fact that I used the standard deviation instead of, and it's using the standard deviation instead of sigma. Standard deviation of the sample instead of sigma of the population, which we didn't know. Okay, so it's actually calculating that for me. So that's my confidence interval, and it is wider as I predicted. I'm not going to worry about the rest of this right now, but that gives you an idea what's going on here. Okay, so you can do these calculations with Excel, SPSS. We're going to be getting into things that are more complicated. For this week, I'm going to put up a homework. I'm hoping that I'm going to put up two homeworks, a 2A and a 2B this week. This 2A is just going to be what we did tonight. It's going to be basically calculating confidence intervals given that you have a sample size, a sample mean, and that the population standard deviation, right? So it should be relatively simple for you to do. Most of them will be, you can use a calculator or Excel, whichever one you prefer. I may give you one example where I want you to use, actually, I'll hold off until the 2B, to give you an example using SPSS, because SPSS always does the correction for using a small sample if you use a small sample, okay, to calculate sigma instead of knowing what sigma is. Okay, so we'll give that a try. Let me go back now. Let me see let's see. In a test, would it be more clear that you indicated something is a population? I'm always going to tell you that. I'm always going to tell you that the population mean is such and such, or the population standard deviation is such and such. Or it might be worded, a sample of 100 people was randomly drawn from a diabetic clinic, and the sample mean, or the mean of those 100 people that were randomly selected, was blood sugar of 102, and with a standard deviation. And notice I'm not saying population standard, with a standard deviation for the sample of 22. Right? So if I don't say it's population standard deviation, you can pretty much assume that it must be the result of a sample. And in real life, think about real life. Do we ever, in real circumstances, know the mean and the standard deviation of an entire population? If you knew that, why would you bother taking a sample? You already know about that population. You already know what the average is for that population. You already know what the range of values for that population. You probably wouldn't bother because you really know that population. So samples are usually taken because you don't know that information and you want to learn about it, either from a observational perspective, where you want to, what's the mean of this population? How varied are the blood sugars in this population? You want to learn about the population. Or the other reason you take a sample is because you want to know you want a good enough estimate of the population mean, so that you can compare it against an estimate of some other population mean, so you can compare the two of them to see if they're the same or if they're different. Okay, and again, you never know the real population mean, so all you know is usually a confidence interval or some way to figure out what the level of confidence that you have that they're really different from one another. Okay, so usually that's not that's only an issue with us in make believe statistics for the next week or so, right? After this week, most of the time we're going to be dealing with samples. We're not going to know population parameters, because the only time we usually know that is when we do a census and we actually do a count to measure what's in the population. So I'm going to put up, probably not tonight, by tomorrow morning, I'll put up a homework 1A. You'll have, I don't know, maybe 3 or 4 problems or something like that are this kind of thing, where where you have to calculate a confidence interval using the values that including, you'll be given the population standard deviation for homework 1A. Homework 1B, 2B, it's going to be a little bit more challenging because you won't know sigma, but by Wednesday we're going to know how to handle situations where you don't know sigma and make up for that error that we're introducing. So let's take a look at just exercise 4 at this last moment. Suppose that we want to know the true population proportion of Americans who are willing to accept the cut and living standards to help the environment in 2010. General social survey. Now I'm going to throw a twist in here, but gird your loins. This is a little bit of a change that we're looking at here. The general survey, but it's not hard. It's not going to be hard. It's going to be straightforward. It's just going to look different. It's going to be the same thing with a different look. The general survey asked a random sample of Americans how willing they were to accept a cut in living standards to help the environment. Out of 1,381 respondents, 496 said that they were very or fairly willing to accept a cut in living standards. 496 out of 1,381. What is the sample proportion that would accept a cut in living standards? Well, based on this sample, it's 496 out of 1,381. So what is that? Let's get our calculator out. It's equal to 496 divided by 1,381. So that is 35.916%, right? Or as a proportion, 0.35, I'm going to call it 0.359 to round it off. So this, you see a normal distribution down there? Just like when you're dealing with a numerical variable, when you're dealing with proportions, right? If you take a sample, repeatedly take a sample, right? Sometimes you're going to wind up above a real proportion that is represented in the population. Sometimes you're going to wind up with a probability that's below the mean, but you're going to find a normal. They're going to find these, since they're random samples, you're going to find them normally distributed. Except that instead of a mean, did I do this the wrong direction? Let's see. Well, this is percentage. 496 says they were willing to accept a cut in living standards. So it's 496. Rebecca, I think I'm right on this one, right? Because I think what you did was you subtracted 496 from 1381, and you found the percentage that were not willing, right? This is asking for the proportion that would accept, right? So it should I think 496. That's from early. Oh, I'm sorry. Okay, sorry. I haven't been glancing over there. When I looked back, I saw that answer, but I get the reference there. Okay, so it's 0.359. So if I go back to my table over here, let's see my graph paper. Where is my graph paper? Boy, things are really getting crowded now. Let me try and open Notebook again. Oh, now this is in the way. Okay, let me try and get there. There we go. Here's my doodles here. I was just reading that people that doodle concentrate better, have higher levels of concentration. It was on 60 Minutes or something like that yesterday, or maybe it was Sunday, CBS Sunday Morning or something like that. One of the news show had a article on doodlers, and there's been some studies that suggest that doodlers actually retain more information than people who don't doodle during a lecture or during a meeting. But who knows? Who knows who knows what the confidence level was for that, right? So we'll deal with that study some other time. Okay, so here is our distribution. I don't really know what the real proportion is for the population. All I know is it looks like, based on what I have, the population proportion for I'm going to guess that it's what we wound up with here, which was, if I can get my calculator back, come on, was 0.359. So 0.359. Okay, now I don't know what the population proportion is. I'm going to call that the population proportion is. All I know is what the proportion is that I found for my sample of whatever 1,300 people, right? That was 0.395. I'm going to give that a special symbol. I'm going to call that P cap. That's my proportion that I got from my sample, and that was equal to 0.359. Okay, now I know that if I went to this population and repeatedly sampled 1,300 people, I would sometimes get more than this, sometimes get less than this, right? But it would be normally distributed around the real population mean. So just like before, when I was dealing with a mean, right? This time I'm dealing with a proportion. So I want to know with some precision. I know it's 0.359, right, is what I got for my sample mean. But how do I know what my population mean is with any certainty? Well, just like before, we're going to start with PCAP, right? And we're going to add and subtract 1.96 times the standard error for PCAP. Okay, that'll give me a 95% confidence interval for the true mean, for the true value of P for the entire population, which might be, I don't know, a million people or something like that, right? So that'll help me. That'll help me estimate. That'll help me understand how precisely I really know it based on this sample. Okay, the problem I have here, I know what PCAP is, 0.359 plus or minus 1.96 times the standard. I got a problem here. This is a proportion. It's not like a regular number. This is a percentage of people that voted for Hillary Clinton versus Barack Obama in the 2000 and 2008 primaries, 2007 or 2008 primaries, right? That's a proportion. Vote this way, vote that way. Or the proportion of people that if I have a population, if I sample 100 people, what percentage of them are male? What proportion of them are male? What proportion are female? Right? It's not really the kind of number that I was used to dealing with before for a standard error. So I need a way to calculate the variability in this situation. In this situation where I got, how many people did I sample? I sampled 1,381 people, right? 1,381 people I sampled. Okay, that's my sample size. Okay, and I got, and I added that 496 were going one way and the remainder were going the other way, right? So now, how do I calculate my standard error? Anybody remember the formula from the lecture that Levi used for the proportions for calculating standard error of a proportion? Okay, again, it's still a sample, but instead of being a numerical value, it's a proportion. It's the percentage of people that met that criteria. Anybody remember that? Okay. Oh, we got it. Oh, great. This is terrific. That formula was the standard error is equal to the square root of P times 1 minus P over N. All of this is underneath, not just the N, but all of this is under the square root sign here. So let's calculate this in this case. Thank you very much, Michelle. Okay, it's equal to the square root of, well, what is it? 0.359. Oops, 0.359 times 1 minus P, right? Well, that's, let's see, 1.00, 0.359 is going to be 1, and this is going to be 4, and this is going to be 9. This is going to be 0.641. 0.641, right, over the sample size, which was 1,381. Okay, I would normally do this in Excel, but I'm going to go ahead and use my calculator to do it here. So I'm going to clear everything, including the memory. So I am going to have point. I'm going to put, let's see, what's the best way for me to do this? I'm going to put 13. Actually, I don't even need the memory. 0.359 times 0.641. That's equal to 0.230 divided by 1381. But it seems like a really small number, doesn't it? But hang on a second. Now we have to take the square root of that. When we take the square root of 0.1 times 0.1, it's 0.01. So fractions get big. When you find square root of them, fractional numbers actually get bigger. So I'm going to take the square root of that number, and it comes out to be 0.01. I'm going to round that to 3, 0.013. Okay, that's my standard error. So it's 1.96 times 0.013. I'm going to take a liberty here now of calling this 2 instead of 1.96, just to speed things up a little bit since we're coming pretty close to the end here. So my confidence interval is going to be 0.359. Let me move this up a little. 0.359 minus 2 times 0.013. Well, what's that going to be? It's going to be 0.026. And 0.359 plus 0.026. Okay, so that's going to be equal to, let's add these together. That's going to be 5. I'm going to subtract that. That's going to be 3, and that's going to be a 3, and that's going to be 3.333. And this is going to be, I'm going to add this now, and it's going to be 5, carry the 1. That's going to be 7, 8, and that's going to be 3. My confidence interval is I'm 95%. Now, what I did was I took a sample of 1,381 people, and I found that 491 of those people were willing to accept this proposition. An average, a proportion of 35.9% of the people, proportion of 0.359. Well, based on that sample size and that probability, I found that I can predict that my confidence interval, my 95% confidence interval is 0.333, 33.3% to 38.5%, 0.385. Now, when I did this, all I knew was this number was 0.359, might be a pretty good estimate of the true proportion for this entire population of people that would go to the polls and vote that way. But this tells me what my level of confidence is. Okay, so I'm 95% confident based on this result that the true proportion of people that are in favor of this proposition is between 0.333, between 33.3% and 38.5%, right? Same thing we did before, except that we had a different way of calculating the standard error, okay? Where when we dealt with numbers, we had a little bit clearer path here. But we're really doing exactly the same process, right? And we're doing this for proportions. And a lot of data that we do is proportions. Percentage of people in this population have diabetes versus the percentage of people in this population. Percentage of drug users that are HIV positive versus the percentage of non-drug users that are HIV positive. We want to be able to compare those. So we have to be able to take a sample and figure out a proportion and figure out how well we understand the range that proportion relates to the true population proportion, which is really what we're interested in. So this is the same problem applied to a proportion. The only other thing I wanted to mention about this is, now, I think that's a good spot to stop. I think that we got a good introduction to this. That this hopefully we'll stop at a point where this makes sense, and I'll post, like I said, tomorrow morning I'll post a brief homework that involves some of these calculations that we just did here, and hopefully you'll be able to do them and feel comfortable with them before we on Wednesday pick this up and go on to the next part. On Wednesday,